Space dazzles us with billions of stars burning at millions of degrees, and yet the universe as a whole is unimaginably cold. If the sun's surface reaches more than 5,500 degrees Celsius, why is outer space nearly frozen solid? It feels like a contradiction, surrounded by cosmic furnaces, but step beyond our atmosphere and you'd instantly freeze. Today, we'll dive into this paradox. Why is the cosmos bathed in light, but still icy cold? How do scientists measure such an extreme temperature? And how does Earth manage to thrive in such a hostile environment? To answer these questions, we must understand how heat truly behaves beyond our planet. NASA's COBE satellite gave scientists the key. It measured the faint microwave radiation left over from the Big Bang and revealed the average temperature of the universe, just 2.7 Kelvin, about minus 270 Celsius, almost absolute zero. But the universe hasn't always been this frigid. In its infancy, it was dense, hot, and violent. Galaxies, stars, and quasars emerged, pouring out unimaginable amounts of energy. Yet, as space expanded, energy stretched thin and temperatures dropped. Today, we live in a cosmos where the void itself is freezing, but blazing stars continue to burn fiercely within it. And here lies the mystery. How can heat and cold coexist so dramatically? The answer lies in physics. Heat isn't a substance floating around. It's the motion of atoms and molecules. On Earth, heat moves in three ways: conduction, convection, and radiation. Conduction happens with direct contact, like when a hot pan warms your hand. Convection moves heat through air or water currents. But radiation, that's the only method that works in the vacuum of space. Electromagnetic waves like light and infrared carry energy across empty distances. Without matter to vibrate, conduction and convection can't exist in space. That's why only radiation warms objects, and why the vacuum itself doesn't store heat at all. Even the sun itself is misunderstood. Many think of it as a giant fireball, but fire requires oxygen, and there's none in space. The sun is actually a massive plasma sphere powered by nuclear fusion. Deep in its core, hydrogen atoms fuse into helium at 15 million degrees Celsius, releasing enormous amounts of energy. But this heat doesn't make space itself warm. Instead, the sun radiates electromagnetic waves outward. Those waves only heat what they strike: planets, spacecraft, or astronauts. That's why shadows in space can drop to minus 180 degrees, while sunlit surfaces soar to over 120 degrees. It's radiation, not air, that determines survival. Astronauts orbiting Earth live this reality daily in direct sunlight. Their suits face searing heat. In shadow, they drop to bone-chilling cold. To survive, their white suits are engineered to reflect solar radiation while insulation regulates their body temperature. Without this technology, astronauts would either freeze or burn. What's fascinating is that space itself has no temperature, only objects do. Temperature requires matter, and in the near-empty vacuum, there's almost nothing to measure. When scientists say space is minus 270 degrees, they're describing what would happen if you placed an object there, radiating away its heat until it nearly froze solid. Across the solar system, planets reveal how heat behaves differently. Mercury, closest to the sun, lacks an atmosphere to spread warmth. Its daytime surface burns at 427 degrees Celsius, but the night plunges to minus 180. Venus, however, is hotter still. Despite being farther from the sun, its thick atmosphere traps radiation, creating an average of 462 degrees everywhere. This runaway greenhouse effect makes Venus a world of suffocating heat. Earth, by contrast, balances perfectly. Our atmosphere filters harmful radiation, retains just enough warmth, and releases excess energy back into space. This balance is so precise that it makes life not just possible, but sustainable. Without this protection, Earth would resemble the Moon, where daytime temperatures reach 122 degrees and nights fall to minus 170. The difference is our atmosphere and active core. Earth's mantle constantly releases geothermal heat, while our molten iron core fuels a magnetic field that shields us from deadly solar radiation. Together, these systems stabilize the climate. But humans are changing this balance. Greenhouse gases like carbon dioxide and methane trap extra heat. They let sunlight in, but block infrared radiation from escaping. This artificial enhancement of the greenhouse effect has raised global temperatures decade after decade, a warning that Earth's delicate balance can be broken. To fully grasp this, consider that without greenhouse gases, Earth's surface would average minus 16 degrees Celsius, far too cold for complex life. Instead, we enjoy a comfortable 15-degree average thanks to this natural system. But with rising emissions, we risk shifting closer to Venus than to Earth's current paradise. And this isn't just theory. Melting glaciers, rising seas, and extreme weather already show what happens when the balance tips. Meanwhile, planets like Mars, with a thin atmosphere, fail to retain enough heat, proving how essential these invisible layers are. Life depends not only on distance from the sun, but on how heat is trapped and shared. Even altitude on Earth demonstrates this principle. Climb a mountain, and air pressure drops. Less pressure means less efficient heat transfer, so it feels colder despite being no farther from the sun. Our atmosphere is structured in layers that interact differently with solar energy. In the stratosphere, ultraviolet radiation creates ozone, warming that band. In the thermosphere, radiation excites sparse particles to extreme temperatures, even 1000 degrees Celsius. Yet astronauts there don't feel hot because so few molecules exist to conduct heat into their bodies. Again, temperature in space is a matter of interaction, not emptiness. Ultimately, the paradox resolves like this. Space isn't cold or hot. It's nothing. Only when matter meets radiation do we experience temperature. An object drifting in deep space cools by radiating heat until nearly frozen. Place it near a star and it absorbs photons, heating rapidly. The universe is a cosmic balance of energy moving from hot to cold, constantly seeking equilibrium. And Earth is the miracle within it. Not too hot, not too cold, but perfectly balanced. Our planet stands as a rare oasis where radiation, atmosphere, and pressure align to make life thrive in a universe that is otherwise silent, empty, and frozen. Now that we've uncovered why space itself doesn't really have a temperature, it's time to dive deeper into how this understanding reshaped our knowledge of the cosmos. For centuries, people imagined the heavens as fiery and eternal, with stars burning endlessly in a warm sky. But with modern science, we discovered that stars are not eternal flames, and the universe isn't a warm ocean of fire. Instead, it is a freezing desert where only the energy of radiation connects matter across incomprehensible distances. This realization not only explained why astronauts face such extremes, but also opened a window into the history of the universe itself, proving that the cold void around us is a remnant of the Big Bang's fading afterglow. That afterglow is what we call the cosmic microwave background radiation. It's like the faint echo of the universe's birth, stretched thin as space expanded. Discovered in the 20th century, this radiation revealed that the cosmos once burned far hotter and only cooled as it grew. Every patch of space carries this faint, cold fingerprint, uniform yet slightly uneven, and those tiny variations explain why galaxies, stars, and planets formed at all. Without them, matter would never have clumped together, and no life would exist. So, when we talk about space being nearly absolute zero, we're also talking about the lingering whisper of creation, the frozen evidence of the universe's earliest fire. But let's bring this back closer to home. On Earth, our survival depends on the thin line between heat and cold. Imagine if our planet were just a little closer to the sun, or if our atmosphere were just slightly thicker. We could easily have ended up like Venus, scorched by an unstoppable greenhouse effect. Or if our air were thinner, like Mars, heat would escape into space and the planet would freeze, making liquid water impossible to sustain. This razor-thin balance is why scientists call Earth the Goldilocks planet. Not too hot, not too cold, but just right. It's a fragile system that relies on countless factors aligning perfectly. Understanding how space works also changes how we look at the future of humanity as we prepare for missions to Mars or even beyond. Astronauts won't just be battling distances and radiation, but the extremes of temperature caused by space's empty void. Habitats will need to shield humans from searing sunlight while preventing deadly freezes in shadow. Future explorers will depend on mastering the very principles we've just discussed: radiation, insulation, and balance to survive on other worlds. And just as our ancestors once learned to harness fire, we now face the challenge of mastering heat and cold in the harshest environment of all, the universe itself. The paradox of a burning sun in a frozen universe teaches us something profound. It reminds us that heat is not everywhere. It's rare, localized, and fragile. Life depends on capturing it, holding onto it, and distributing it. Earth does this brilliantly, acting like a cosmic thermostat. But as humanity alters the atmosphere with greenhouse gases, we're testing that balance by understanding space, heat transfer, and cosmic temperatures. We're not just studying the universe, we're learning how to safeguard our only home. Because in a cosmos that is silent, dark, and cold, Earth shines as one of the few warm, living places where balance means survival.